Hi everyone, welcome back. In the last video, I arrived at the dimensionless term for delta and x as a function of Reynolds number. I do want to make a small correction, which is this term right here. So square root 30 is actually not 1.48, it's actually 5.48. Okay. That's the only correction I want to make. However, if you want to increase the accuracy of the problems, it's always a good idea to use square root 30 instead of an approximate term. So what I mean is this term right here on the left is more accurate than, say, delta over x equal to 5.48 over Reynolds x to the power 1/2. Okay, we'll use it again, you see, in the next part. So that's being said, let's see what's the next part asks us to do. So part B, they ask us to show that tau w over 1/2 rho vx infinity square equal to 7.73 plus me over square root of Reynolds number, right? Okay, let's go ahead and show the problem, the author, that we can get this amazing expression. So we start with something we know already. So y'all recall that, okay, we know that tau w equal to 2 times mu times vx infinity over delta, right? Where can we find that? I think it's somewhere here. There you go. So it's basically when we take the derivative at y equals 0, that's where we arrive at. Okay, so let's divide it. So, oh, by the way, to show that something equal to each other, you can turn the left hand side to the right hand side. Okay, so let me write. So left hand side LHS equal to tau w over 1/2 rho vx infinity square. We can substitute this in, so we get 2 times mu times vx infinity over delta over 1/2 rho times vx infinity square. Let's simplify it. So vx here cancel out, this become vx infinity, so you get 4 mu over delta times rho times vx infinity, right? Okay, here is the way it get interesting. We need to do some manipulation, right? So let me further. We have to make Reynolds number appear. Remember, that's the goal. You see, our final result on the right just contain a number and the Reynolds number, Rex. So we have to make sure the Reynolds number appear. So let me go ahead and let me divide both sides by mu. So this continues to equal to 4 over delta times rho times vx infinity over mu. Okay, I'm gonna go ahead and make try my best to make Reynolds number appear. So this continues to equal to 4 times delta times rho times vx infinity times x over mu divide. If you times x, you have to return it. Borrow x, you have to return it by divide by x. So I make a note right here. Equal to 4 over. Okay, do you see this term right here? This term right here is actually Reynolds number, right? So what do we have? We have delta over x times Rex. Beautiful, beautiful, beautiful. Now, let's see what can we do with this. Delta over x times Reynolds number. I just want Reynolds number to appear. That's the goal. I just want everything to level Reynolds number. Oh, I remember we have an expression for delta over x in terms of Reynolds number. Y'all see it? You see the beautiful yellow color over there? Exactly. So I will make a note. So recall, we have delta over x is square root of 30 over Reynolds number. So I'm going to substitute this in. So our left hand side continue to be equal to 4 over square root 30 over rex times, wait, rex 1/2. Square root, sorry. So square root, yeah. Square root of rex times rex equal to 4 over square root 30. A number divided by a square, so it'd be rex square root. So I'll rewrite like this: 4 over square root 30 over square root of rex. And what is 4 over 30? Let me use my calculator. It is approximately 0.73. And what is square root of a number? Square root of a number is that number to the power of 1/2. So square root of rex, we get rex to the power of 1/2. And this is exactly the right hand side. So we have successfully demonstrated the left hand side equal to the right hand side. We have successfully demonstrate that the left hand side equal the right hand side. Wonderful, wonderful. Okay. All right. So let's see what's the next part of the problem. So let's move on. So part C. Okay. Okay. What does part C say? Part C, they give us this term, tau mu, and then you have a dash over here equal to 1 over L times square integral from 0 to L tau w times dx, and they ask us to find the Reynolds number in terms of L. Okay. Sorry, I apologize. That's not what the problem asks us. Let me organize this a little bit. So this is what they give us. This term is called the above term is called, what does this call? It's called average shear stress per unit length. If you want to read more about the definition, you can check out for more info about the definition. You can check where you can check equation 3.19. Okay, page 127. And if you use the electronic copy, you should be page 146 out of 07. Okay, they give us this average shear stress per unit length term, and they also say that Reynolds number as a function of L with respect to L. So what is it? It is rho times Vx infinity times L over mu. So basically, you see like this term right here correspond with this term right here. Wonderful. What do they ask us? So the goal is to find average shear stress over 1/2 rho Vx infinity square. Okay, you see the other problem we find on part B, we find shear stress. We have demonstrated that shear stress over 1/2 rho Vx infinity square is actually a function of Reynolds number. It's actually equal to 0.73 over square root Reynolds number. Let's see if we can do the same thing for the average shear stress. And we can arrive at something very, very nice. Okay. I'll continue doing that in next video.